Now we will talk about different parts of the robot. Here we have the robot manipulator or arm. It receives the name of manipulator or robot arm, the set of mechanical elements that promote the movement of the terminal element, so the gripper, crank, or tool. Within the internal structure of the manipulator, on many occasions, the driving elements, gears, and transmission that support the movement of the four parts that generally make up the arm are housed. One part is the body, then the arm, the grease, and the terminal element or gripper. Remember, the four rigid elements of the arm are related to each other by means of joints which can be rotatable when the allowed movement is rotational. The robot grease is used to establish the orientation of the end effector. Robot grease usually consists of 2 or 3 joints that almost always consist of capital R and capital T type rotary joints. This figure illustrates one possible configuration for a 3-axis grease assemble. The 3 joints are defined as follows. First, roll, using a capital T joint to accomplish rotation about the robot arm axis. The second is pitch, which involves up and down rotation, typically using a capital R joint. And finally, number 3, the yaw, which involves right and left rotation, also accomplished by means of a capital R joint. A 2-axis grease typically includes only roll and pitch joints, so capital T and capital R joints. Here we have the controller. This name is given to the device that is responsible for regulating the movement of the manipulator elements and all kinds of actions, calculations, and information processing that is carried out. The complexity of the control varies according to the parameters that are governed, and the following categories may exist. First, we have the position controller. It only intervenes in the control of the position of the terminal element. It can operate in point-to-point mode or in continuous mode, in which case it is called continuous control of trajectory. Second, we have the kinematic control, when in addition to the position, the speed is also regulated. Third, we have the dynamic control. The dynamic properties of the manipulator, the motors, and associated elements are also taken into account. And finally, we have the adaptive control. In addition to those indicated in the previous controls, the variation in the characteristics of the manipulator is also considered when varying the position. Robot joints are actuated using any of 3 types of drive system: electric, hydraulic, or pneumatic. Electric drive systems use electric motors as joint actuators. For example, servo motors or stepper motors. The motors are connected to the joints either using no gear reduction, called direct drive, or with a gear reduction to increase torque or force. The hydraulic and pneumatic drive system use devices such as linear pistons and rotary vane actuators to move the joint. Pneumatic drive is typically limited to small robots used in simple part transfer applications. Electric drive and hydraulic drive are used on more sophisticated industrial robots. Electric drive robots are relatively accurate compared with hydraulic powered robots. By contrast, hydraulic drive robots can be designed with greater lift capacity. The drive system, position sensors, and speed sensor if used, and feedback control systems for the joints determine the dynamic response characteristics of the manipulator. Sensors used in industrial robotics can be classified into two categories, internal and external. Internal sensors are components of the robot and are used to control the position and velocities of the robot joints. The sensors form a feedback control loop with the robot controller. Typical sensors used to control the position of the robot arm include potentiometers and optical encoders. Tachometers of various types are used to control the speed of the robot arm. External sensors are external to the robot and are used to coordinate the operation of the robot with other equipment in the cell of the flexible manufacturing system. In many cases, the external sensors are relatively simple devices such as limit switches that determine whether a part has been positioned properly in a fixture or that a part is ready to be picked up at the conveyor. Other situations require more advanced sensor technologies, and we can include different sensors as tactile sensor, proximity sensor, optical sensor, machine vision, computer machine vision, and other sensors. A miscellaneous category includes other types of sensors that might be used in robotics, such as devices for measuring temperature, fluid pressure, fluid flow, electrical voltage, current, and various other physical properties. Finally, we will see some advantages and disadvantages of industrial robots. Industrial robots offer many and important advantages to be considered their implementation within a flexible manufacturing system. Some of the most important are mentioned here. They are safer, stronger, and can work continuously. They are less likely to make mistakes than humans. They reduce manufacturing costs. As many of them are reprogrammable, they can perform different tasks. They can replace humans in dangerous and tedious tasks. They play an essential role in many flexible manufacturing systems. However, they also have some significant disadvantages. Its cost is high. They displace labor. His work area is limited and little fault tolerant. The mechanical possibilities of robots depends not only on the number of their axes, but also on other characteristics. The most important ones are handling load capacity, useful volume of work, travel speed for each axis, positioning precision, repeatability, and operational safety. Although the robot is itself a flexible element, it is also necessary for its gripper hand to be efficient and flexible to grasp all the parts to be machined in the cell. It can happen that sometimes it is necessary to change the gripper to adapt it to very different parts. In this case, it will be necessary to have an automatic gripper system for the robot.